I think, let me see if I watch the beginning over here, it'll have the yes, yes, it does have equation of motion written down. Okay. So that is the equation of motion. And so let me copy that over. If you want to see the whole the whole derivation of equation of motion, you can watch the lecture. For now, for the purpose of this virtual class session, I'm just going to copy that expression. It gets that fancy sounding name, equation of motion, because it's really what it is. It's a single equation that characterizes the entire system. It relates by motion, I guess in the most general sense, we are talking about the position as a function of time. Once you know other parameters of the simple harmonic oscillator, knowing this is really what will nail down everything. Once you know the position is a function of time, it's a easy single step to calculate velocity as a function of time. And once you have position and velocity, you have everything you need in addition to parameters like spring constant. You have everything you need to calculate um, the potential energy, kinetic energy. So when you are solving a system like simple harmonic oscillator, the goal is to get to this functional form of the position. And when you work through the physical setup of the simple harmonic oscillator, you come to this differential equation, second order differential equation that says second order time derivative of the position is equal to minus k over m times the function itself. This x looks like a variable, but it's x as a function of time. So whenever you see X, just to be aware here that it's a more complicated object than just a variable. It's a function of time. So this is the equation of motion. And now I think if this had been something different, something like maybe let me think of a simpler differential equation that I can imagine even being seen in Math 3A, maybe, and definitely by Math 3B. So if you had something like this, if instead of second order, if this had been the first order derivative is equal to minus k over m x of t, this is the kind of thing that you can actually solve. There's a method called the separation of a variable that actually works a lot. It kind of, you look at, okay, I have a differential here, I have a differential here. If it would be nice if I had them on the opposite sides, so that I have some integrand dx is equal to some integrand dt. Then I can imagine integrating both, and that'll get me something that if I plug it back in here, then that'll be the solution. So along that line of thought, you can do something like this. Okay, let's just, I guess it's okay. So this is the physicist way of doing it. We abuse the notation. We kind of treat this like a fraction. I know it's not, but in this particular case, I know you can multiply both sides by dt. Now, it's not exactly right, but this particular abuse of notation doesn't harm anything, so I'm just gonna do it. So, cancel the dt here. I'm doing something wrong, but the end result is fine, so I'll just keep going. Dx is equal to minus k over m x of t dt. Now, if I just do an integration here, I know I'm going to run into trouble because I have expression x as a function of t. And if I just integrate here, it'll be integration with respect to t, but this is an unknown function, so I don't want to do that. That's where separation of a variable comes in. So in the separation of variable technique, you try to identify your variable and you try to put your variable with the matching differential. So I need to move this x over to the other side. So let me do that. When I do that, this is what I'll get. Dx over x, it's still as a function of time, but I'll just leave it as x for now, is equal to minus k over m dt. And now this is the nice thing. When you look at the left-hand side and you look at the right-hand side, left-hand side, everything is in terms of x. On the right-hand side, everything is in terms of constant or t or no t. So this is an expression that I actually do know how to integrate. So when I integrate both sides, this is what I get. Integrating the left-hand side. And I prefer to always do definite integrals like x initial to x final, and the right-hand side will also be from time initial to time final. Doing definite integral helps you avoid certain mistakes that are easy to make when you don't pay attention. Um, and it has to do with the integration constant. It's the sort of thing that calculus students forget all the time. Let me just move this all up so that I have room for that. So when I do integral of both sides, then on the left-hand side, it's not necessarily all that a simple integral. It's a, 1 over x. So that's not just a power law thing. I have to remember that, oh, this is a natural log of x, evaluated from limit of xi to x final. Right-hand side is simpler. It's just constant, so it is power law. Just multiply by t. So minus k over m. Uh, T evaluated from T initial to T final. And I can make things easier for myself by just saying my T initial was equal to 0. I'm not sure if I can, I'm pretty sure I can't say that X initial was equal to 0. That'll result in some issue here, so I'll just reserve that. So with that, what I have is, okay, lateral log of, I'm just gonna imagine plugging this in. Then what you have is ln of x final minus ln of x initial. You do the logarithm algebra. Hope you can do that or look up logarithm algebra. When you're done with the logarithm algebra, this is what you have, x final over x initial is equal to the t initial. I said that will be 0, so it will be just minus k over n t final. And I can even solve for x final as a function of time. And x initial will be some constant. And when I do, I might even get something like, after a couple more steps, x final as a function of time is equal to x initial, let me call it x naught, initial value of x, times exponential of minus k over m t final. And this actually makes perfect sense. I can plug it up back into my hypothetical equation that I could have had. Dx over dt is minus k over m x of t. When you imagine plugging it in here, you take one derivative, you get this coefficient out through the chain rule, and then you have the original function left. So in this hypothetical solution, I didn't appeal to anything that mathematician would have a serious problem with. I mean, other than a slight bit of abuse of notation, but in math classes they do teach you separation of variable, so it's not like I did something seriously wrong. I might not have fully justified my steps, but it was more or less fine. Now, what I want to say is that this entire approach that easy enough to introduce in the first year of calculus and and in this first semester of mechanics, this doesn't work when you have second order differential equation, um, because the whole abuse of notation that I did, I can't multiply by dt squared. Like, that's not a thing that would result in an expression that I can integrate. So the whole solution approach, maybe the only approach towards solving differential equation that you might have learned before Math 3F, it doesn't work. You can't use it. So that's why in the lecture you see me doing what we did, which is you just guess a convenient answer and you plug it in, because you can always plug in your guesses and see if your guess leads to the some reasonable result. And when you know what to guess, that's easy to do that, and it really works out well. So now normally we would be just be left there. If working these things out by hand is the only tool that I have, then all right, that's all we can do. Nothing more. So in the lecture, I think you've seen me guess as far as maybe this much. To say x as a function of time is some amplitude times the cosine of omega t plus some phase factor. Like if you happen to have that convenient guess, you can guess that and it somehow will magically work out. And what I want to do now is because we have access to this wonderful tool of computer algebra system, I want to try a little bit of a more rigorous approach that is not necessarily harder because, well, I say rigorous, but the rigorous or hard part, it's done in the software. There's a there are algorithms for working out differential equations of a certain type, and I'm just going to use this. Let me just to make the text a little bit larger. So so yeah, let's so I will need to work through that. I haven't really tried this before, and I'm not as familiar with SageMath as I am with Mathematica because I have less experience with it. I do know in general what kind of things computer algebra systems ought to be capable of. So I might need to, from now and then, Google stuff. So if the need comes up, I'll do that. I did Google up some stuff before the session started so that I'll at least to know something to do. So let me start here. So I have this equation here. So I see I'm going to need some parameters, k, m, and t. So let me declare those first. Variables k, m, and t. These are just the symbols that I'm declaring in my SageMath environment so that when I do this, SageMath knows what it's dealing with. Not how if I just type A, it complains that it's not defined. And I did Google before about solving ordinary differential equation with the SageMath, and I'm told the function that you use is dissolve. Uh, what? Oh, okay. It- Uh, okay, that is that. Oh, I see. I see. Okay, let me do it this way. Help dissolve. I think that okay. So this is the documentation on that function. What it's saying is dE. I guess that's the differential equation. D var is that the differential equation variable? I don't know. So sometimes some functions are simple enough that when you look at this function and the function parameters, it makes a sense. Dissolve is, I think, oh, I see, there it is. It is complicated enough, even with this question, oh, dependent. So, okay, so d var here would be x. T is my independent variable, x is the dependent variable. Yeah. Now, even reading this, I'm not 100% sure how it works. Now, one of the nice things about these documentations is they will have some examples, and sometimes the examples tell you more than what the description of parameters does. So I'm just scrolling down to the examples portion. Okay, yeah, output, symbolic equation. Okay, examples. Okay. Okay, that looks simple enough. So x is the independent variable. I already declared the t. And oh, wait, so I need to, let me just write on the side so that I have, when I exit the documentation thing, it'll kind of disappear. So I'm just going to write this on the side. So y equals function y. I guess that declaration is needed to tell SageMath that y stands for the function, not variable. Okay, and then the syntax for dissolve would be dissolve. Oh, right. If yx tells you it's a derivative of y with respect to x, and then some other things, and then the dependent variable is what they want here. Okay, I think that makes sense. So I'll have to change this up for our case, where we declared these variables already, k, m, and t, and what we need to declare in addition is our function, which is x as a function of time. So we need to say x is equal to function x t, I think. Okay, that seems to make sense. And one of the things that's nice about this, let me just refresh the screen. One of the things that's nice about this interactive environment is it has something called a tab completion. So X is an object that's known to SageMath. It has certain properties, certain bound methods. So when you do X period and then press tab, a few times, that'll access this tab completion. It tells you what kind of things can be done with this function. So sometimes this is as useful as a documentation in kind of knowing what kind of things can be done. This is a feature of something called object-oriented programming, and I think that this is one of the reasons that object-oriented programming in the interactive environment is so popular, because it's so user friendly when you are new to this. Like, and what does that do? I don't know. All right, yeah, I don't know. I don't want to do it. Okay, so I have that. I have k, m, and this is an object that mathematical. Sorry, SageMath knows what to do with. Like a is not declared, so it can't do anything. And I have t and then x. Okay, so the differential equation I would need is basically this equation here. So the function diff is basically what I need, but I don't know the syntax for diff function. So I'm just gonna say help diff. What is it? The derivative of f. Okay. I want one second order. So let me see if there's a way to do the second order derivative kind of in a more compact way rather than trying to chain a derivative twice. I hope there's a way to, yeah, repeated differentiation, um, derivative. I see. So I can either do this way, f with respect to u once, then twice, or I can specify the order of differentiation. Okay, I think I'm gonna do that. So I think I'm pretty sure diff and derivative are synonyms. So I'm gonna do diff of x with respect to t, second order. So that's the left hand side here, and I'll say okay, that's equal to minus k over m times x as a function of time. Let me just press enter and see what I get there. Okay, good. SageMath recognizes as some kind of expression. Okay, so now the syntax for dsolve is differential equation solve is this equation that's one of the inputs, and say that I want it solved for x. I hope unable to. Okay, all right. Let's specify independent variable. Is this how we specify? Okay, let me see. I don't know the syntax. Independent variable. That's I think ivar. Um, yeah, independent. Okay, so will need to specify that as a parameter. So, this is the syntax. First the parameter, second parameter. That's all what it's expecting. And for the independent variable, I need to say ivar is t. Okay. Okay. The first time you run these things usually takes a little bit of time because I think SageMath, it runs under virtualization in Windows, so it has to initialize some stuff. And what? Maxima requested additional constraints using, assume command. Yeah. So yeah, is k times m positive, negative, or zero? Yeah. I can see. So it's a. So I should say it's positive. So since that's the form of the question, let's do it this way. Assume that k times m is positive. And it comes down to the classes of solution that fits here. It really does depend on the sign of this coefficient. And I guess as I was writing this down, I was implicitly assuming that K and M are both positive, so their product or their ratio would be positive. But this is a feature of computer algebra systems. They are written by mathematicians, and they tend to assume very general things about variables. I'm pretty sure they were trying to find a solution, assuming K and M might be complex. So, gonna enter that assumption. So that should help it solve, I think. Oh yeah, that was quick. So yeah, that's the solution. Let me just refresh the screen so that yeah, that's the solution. It has so it's giving these parameters that they are what do you call it? They are related to integration constant. um I don't know the terms for this, but both of this underscore k2 and underscore k1, they are both they are coefficients. They are usually constrained by what the initial condition is. So when you have an equation of motion like this, it specifies the motion of the oscillator for all time, assuming you know the initial conditions. So you might specify something like this. Let me say, okay, my initial conditions. Oh, okay, what's behind it? Oh, yeah, let me just close it. Okay, so let me give it kind of the initial conditions that you see in the lecture. So in the lecture, I first pull down on the mass and then let go. So at what's reasonable for me to say is that at time equals 0, my initial position at time equals 0 is equal to minus x naught. I'm trying to make x naught positive, so this is describing how I've pulled down by some amount of height. And let's see here. So I think with that output, what I should say is that let me do it this way. So x sol for yeah, I think x sol is a function. X sol is a function of time. So, let me just do it this way. So dissolve is going to be x solution. And I think I can plug in time equals 0. So substitute uh, time is equal to 0. Yeah. So I can do this. I can say, okay, at time equals 0, um, my value of x at that time is equal to minus x naught. Oh, yeah, right. I need to define my variable. um, um, Now, when you look at here, so you say, okay, that constraint will constrain what K2 is for me. So I can say, okay, so my solution is at so my replacing my K2 with minus X naught. And when I do that, this is the problem that you will see. Oops. Really, is that how it works? Uh, Let me just give it this a try. I don't want to define K. Okay. Sorry, I'm not experienced here. Um. Oh wait, yeah. Sorry, that wasn't right. I. Okay. Okay. Good. 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 It somehow replaced the K2 with a minus X naught. And when I do that, you see that we are not done. My solution still has an arbiter or a coefficient that still needs to be determined. And I hope this is where you see the generality of this solution. So when you look at this solution X, or I guess X SO, this is it covers the general class of solutions, and there's a reason this has two integration constants. It is connected with the fact that there's it's a second order differential equation that it's coming from. And when you have two integration constants, a single condition like this is not sufficient. And when you think through it, there was something that's so intuitive to us that we just assumed it. We didn't bother specifying it. But what we need to specify is we need to specify what the derivative of x is at time equals 0 as well. We need to specify the velocity. Now, once you think through then you realize, of course, that velocity, as I'm releasing it from rest, is equal to 0. So that is the one particular initial condition you can set to have that oscillation that you see in lecture. And you can, once I state that, then you can see, oh, yeah, an oscillatory motion could be at the same position at the same time, but if it has some initial velocity at that position, then it would be describing something different. So, okay, we need to do that. We need to um, try to plug that in. So what did I do before? So before I had this equation, and and when I set this, it just okay. And what we need is let's see. I think because this is at k to more or less independent of other things in this particular case, I think I can do a bit of a more hacky method that still works. So the condition we are trying to set is we want to say derivative of xo with respect to t. That's my first derivative, velocity. And when I substitute in t equals 0, I want that to equal 0. Okay. Then I get this combination of expressions, which means, okay, so k1 is equal to 0. Okay, then I think I can do this. Let me declare a variable k1. And what we can now say is, okay, x so substitute in these two coefficients. K1 is going to be 0, and k2 will be minus x naught. And that is my, is it specific? I think it's called a particular solution. This is my particular solution to this differential equation with these initial conditions. So this is my solution. Let me put this in as I don't know, x a um, particular solution. Um, Yeah, so that, can I plot this? I think I might be able to plot this solution as a function of t. Oh, wait, I need to plug in some numbers, because if I just did this, I'm pretty sure it's gonna complain. Because yeah, variable x not found and all that stuff. So what I need to do is I need to substitute in x now. Let's just make it 1. Um, let's just make everything 1. I think we'll be fine with that. Um, just to plot something. So let's plot this as a function of time. Do I need to specify the range, or will it just choose something reasonable for me? Oh, let me just give that a try. And um, oh yeah, there it is. Okay, it picked something. It wasn't reasonable. So let time start from 0, go from 0 to, I don't know, 10, in some arbitrary unit. Plot t. Okay, I don't know the syntax for plot, so let me look it up. X. How do I specify the x min and x max? Is there an example? Plot. There it is. Um, so those are where. There it is. I think this is what I want. Okay, I think that makes sense. So here I need to replace t with t 0, 10. T from 0 to 10 what in whatever units. Yeah, and this looks oscillatory. It oscillates up and down, and yeah, that's fun. Um, so and now that we have a solution like this, we can also do different initial conditions and all that. So I think yeah, and I guess the advantage of this approach, there are two advantages. One is that when we were just guessing the solution, um, we couldn't be sure that the what we guessed was a unique solution, and that's sort of why. So here, if you had guessed a times cosine of omega t without the phi, you'd have seen that, oh, that's a solution, and then if you stop there, you'd have missed out certain possibilities. And it takes kind of experience and knowledge to know, oh, I need a second parameter in case my initial conditions require the parameter for agreement with that initial condition. Um, when you have computer algebra system simply solve for you what X solution is, through this expression that you type in, then the solution you get, you saw how it was trying to work it out generally. This is the general complete solution. This second order differential equation actually does have two solutions. It has this as one possible solution. It has this as a second possible solution. And what this general solution is a linear combination of those two possible solutions. And it covers all the bases. So that's one advantage, that when you have computer algebra system rigorously working at the solution, then that's really the final word. You didn't miss anything. That's one advantage. There's a second advantage, which is that with this tool, we can now do things that we couldn't do. And at this stage, even just guessing a solution would have been too hard. Let me show you what I mean. So and your textbook actually covers this that we kind of skip because we don't have tools to deal with. It's sections 15.5 and 15.6. Forced oscillation might be a little bit more tricky. I'll leave that for another time. But damped oscillations, I'm pretty sure with a slight bit of modification to what I just did, I can get solutions for damped oscillations. So when you look at the damped oscillations, it should work as some equation of motion. Yeah, there it is. So this is the equation of motion for damped oscillation. Let me just leave it in this form. So I'll just copy it over. You can see the connection between this and this here. So just before I erase my original equation of motion, this second order term, it's here. This term that goes linear with the function itself, that's here. So really the one new term here is this damping term. And that does come from this additional force that's providing the damping force. So let me copy over that form of the equation of motion, and we'll work out the solution for this damped simple harmonic oscillator. And second order derivative plus this first order derivative, and I think B is meant to be positive, plus kx is equal to 0. So this is my damped simple harmonic oscillator equation of motion. Okay, so let's try solving it. And you can see that in your textbook, they don't try to solve it because, again, it's so hard to do. This is give you the solution. Let's see if we get the same answer. So here. Okay, so the differential equation we are dealing with this time is, I need to declare B as one of the parameters. Um, so I have n times differ derivative of x with respect to t, second order, plus b times derivative of x with respect to t, first order, plus k times x is equal to 0. That's my differential equation. And what I want to do is solve it um, for function x. And I'm sure it's going to complain again about the independent variable, that's t. Okay, let's see what it does. Oh, yeah, yeah. I figured it would do that. So the reason it's complaining is because it, yeah, this is actually a fairly special combination. You can see this in the textbook. So when you look at the textbook section on this, they give you the things about critically damped, underdamped, overdamped situations. And yeah, it comes here. This is the condition. So the solution that they are describing here, this is an underdamped case. uh, in which case this difference, which is in terms of sign, it's equivalent to this here. When this difference is positive, that's when you have underdamped solution, and the underdamped solution looks like this. And I think there's they should also talk about underdamped, and when this is equal to 0, that's the critically damped case, and this is the critical damping, and the overdamped case is this one. So let's see if we can reproduce each of these plots. So so in order to reproduce the underdamped case, first we'll say, okay, let's assume that 4 times k times m minus b squared is positive. That'll be the, I hope, underdamped case. So let's try to solve it again. And we get that. um, okay, so it's got two parameters, k2 and k1. Let's try to put in the same initial condition as before. We started out with some displacement and then we let go. So some initial displacement. Let's make the displacement positive. And the initial velocity will be 0. So we have, let me put this as my solution. And x solution with t equals 0. um, yeah, I want to say that's equal to x naught. Yeah, so k2 is x naught, good. And the substitution, wait. Oh, I think I can take a derivative this way. Derivative with respect to t. I think that's all. Yeah, I think that I can do. Substitute in t equals 0. So this is specifying the velocity at time equals 0 is equal to 0. So, oh wow, that's complicated. Let's solve that for solve this for k1. And put this into K1 sol. K1 sol is that. So okay, it's not that simple as it was before. So this is what we have then. We have so x particular solution is x solution where I'm substituting in these two values. My K2 is simple, it's just x naught. And my K1 is apparently this complicated thing here. How do I specify this? Let me see if I can. K1, so mm, wait, let me do this again. So I need access to the tab completion to figure out what my options are. I was hoping there is an expression to just take the right hand side. Let's see here. Partition combine. PHYS, um, um, there's just a thing for right hand side. Ah, yeah, I see LHS for left hand side. So there, yeah, there's a right hand side. Okay, good. Uh, K1 sold that right. Okay, so as a function, okay, good, good. That is exactly what I'm looking for. Um, so left hand side. Oh, and I see that so right hand side has this dependence on K2. So I'm going to do it this way. Okay, I think I got it. So okay. um, so we already have this. This is one of the things that we'll put in. Wait, not this. We have this. Yeah, it's K2. Okay. So for X particular solution, I'm going to take X solution and I'm going to do this substitution one at a time. So that first I can substitute in what K1 is. So I'll say K1 is K1 sol dot right hand side. This will plug in this expression for K1. And then after the substitution is done, if there's an expression, I'm going to do another substitution on that expression, replacing all instances of K2 with X naught. Um, so that should give me an expression for a particular solution. And it looks complicated. I think I can simplify it a little bit more. Maybe full simplify. We'll see. Um, a little bit. I mean, I got M. So here's something that's oscillating as cosine of something as a function of time, okay. And I have a b times the sine of, okay. And this is the one of those cases where, so sometimes computer algebra system doesn't give you a very intuitive looking answer. Yeah, it's something that you just have to deal with. It's this is really one of the reasons you might want to know how to do calculation like this by hand, because when you're doing it by hand, you can get a more human readable solution like what's in the textbook. Um, but let me just continue with this. I mean, it has all the parts. It's got exponential. So I have some faith that it'll work out. To make this more human readable, let me plug in some numbers. Now, what we did assume is we assumed this is positive. So, I think if I put in K and B all equal to value 1, this assumption will hold. So I'll say X part sol, I'm going to substitute in all these parameters. Uh, M is equal to 1, K is equal to 1, B is equal to 1. Let's see, what other parameters do we have left? We have X naught. Let's say X naught is also equal to 1. Then I think that's all the parameters. Okay, so this is something we can plot. Let's plot. Plot this as a function of time from 0 to 10, same as before. So this is quite similar to our previous simple harmonic oscillator, except that we put in a damping that matches with B equal to 1. Let's see what we have. Oh, yeah. Okay, that damps down pretty quickly. Let's try a different value of B. Let's say we want to put in, I think a higher value of B means more damping, so let's make this smaller. So it's less damped. Oh, yeah, yeah. And we can actually plot this out to a larger amount of time to see what the oscillation will look like over a long period of time. Yeah, that's the damped simple harmonic oscillator. Um, and if we make the b smaller, you can see how this resembles. So this is a way to model a real world oscillation. So the b parameters modeling things like air resistance that would cause energy to be lost. Now there's at some point, like if a b is too large, I don't know if it'll let me plot it at all. We'll see. Yeah, we ran into trouble because I put in a value of b that didn't match the assumption we put in. So this assumption, it constrained what my B could be. I wonder if so with a K, I think a B is equal to 2 is what will make this left hand side equal to 0. Let me just give that a try to see just what this will do. Wait, plus. Um, I don't know. There it is. Let's just put in B is equal to 2. It might still complain. Yeah, there's a division by 0. Okay, let's do this. Let's get a new solution. So we can enter a new assumption. Let's assume that this is now equal to 0. Can I clear assumption? I guess I assumed my additional assumptions would just override the previous assumptions. There must be a way to list existing assumptions and maybe clear it. Okay, okay, forget. Yeah, let's use forget. Forget. Forget my assumptions. Now enter new assumption. And where's my previous command for the solution? Uh, okay, I think this is my previous command for solution. Yeah, let's see what we get. Uh, uh, Using is B zero or non-zero? Yeah, we should say B is non-zero. In fact, let's assume that B is positive. Because we are looking for a critically damped case, so we should have a positive non-zero B. Okay, we got an answer. Oh, uh, uh, that that is just an exponential. No, it's not just an exponential. There's a okay. So let's go through the same series of steps, and as you do this over and over, there's a way to automate it, make it more systematic so that you don't hunt and peck for expressions as much. But let me just do this in a less efficient way for now. So when I'm plugging in t equals 0, I want that to the x value to be um, some parameter, initial value. And when I for the derivative of this with respect to t, when I substitute in t is equal to 0, I want that to be equal to 0. Okay. Um, all right, so it looks like this also used. So k2 sol is equal to solve this for k2. Um, yeah, k2 sol. Um, Yeah, and I can use the right-hand side to get that expression. Okay, so I can do this. X particular solution is, I take X solution, and I have to do this in right order. I have to substitute in K2 first, so that I can, when I plug in K1, it just substitutes everything. So substitute in K2 is equal to K2 solution, the right-hand side. There's probably more efficient way to do this. Again, I'm not super familiar with the SageMath. K1 is equal to X. Okay, so that should be X particular solution. All right, I can imagine plugging in. Oh, here I have to be careful. It looks like I can plug in B. Oh, and I think the assumption that we had, that that difference being 0, it constrained the value of K enough that it's not even in this expression, just in terms of B and M. So we'll just say uh, my values of mass and B are such that the mass is still 1, and now B can be 1. And this will constrain K in such a way that everything else works out. And okay, and I need a value of x naught, call it 1. Yeah, and that's something I can plot. So I can imagine plotting this as a function of time from 0 to 10. And that's the critically damped case where the thing comes to a stop over. I mean, it does take an infinite amount of time because it comes to a resting the equilibrium position asymptotically. But the critically damped case is where it will come to rest the quickest possible way. So, have this picture in mind, or whether I'll just have this on the side for the critically damped case. And let's work out the on overdamped case. So overdamped case is where in this assumption you say this is not zero, it's now negative. So let me first forget, or yeah, let me just forget, and then bring in that assumption. Say this is now negative, and let's see if we can get a solution. Okay, yeah, that was quick. Just got a solution. The solution is that I don't know. Let's just plug in the values, or go through the same motion, which is I'm going to substitute in time equals 0 and say that at 0 I'm starting out at some initial position. Oh, and now that gives me hmm. All right, I might actually have to do a full-blown solution thing. Let me see here. Derivative of x solution with respect to time at time equals 0 is x equal to 0. Okay, so I have a genuine system of equations. So I have to have the system solve for that. So this is the way to do it. I'm building up my system of equations in a programmatic way. And this was really the way I should have done it from the start. So this is my first equation that comes from imposing the initial condition. This is my second equation that comes from imposing the initial condition. This is my system of equation. And what I want to do is, okay, solve this for me in terms of K1 and K2. So yeah, that's the solution. I guess, how do I want to do it? Wonder if it's giving me some array stuff. I think this is the solution array. Wonder if this works. If this is the solution array for the constants, can I do XSOL subs? So I've been putting in dictionary as a parameter to this, but I think a substitution function might accept something like this as well. Yes, it does. Yeah. This is the smarter way to do it. Okay, now I can plug in the other parameter values. So the parameters I put in, they have to be consistent with this assumption, which means my b value has to be reasonably large. So I can do this xsol subs ksol, and then I substituted in the parameters. For consistency sake, I'll say my m is still 1, my k is still 1, but my b will be, I don't know, something large like 3. So it's a slightly overdamped case. I think a 2 was the uh, critically damped case. So, all right. So, oh wait, this is not gonna be a good comparison. Um, Mainly because the value of b I'm using here is different from the value of the b that corresponds to this picture. So I have a feeling when I put everything in, it won't quite work out right. But well, let's work this out. So I have that expression. This is something I can plot as a function of time from 0 to 10. 0 to 20. And let's see. Oh, wait, X not. I need to plug in X not. Okay. Yeah. So these two are not comparable right now because the b value is different. So I'm comparing apples and oranges. But I got I got the over them to case. It's I got an answer. And it's a lot of fun to play. Because I used up the whole time. I wanted to do other things, but I think computer algebra systems are really wonderful because it lets you explore things that are really too difficult to explore without being super genius at math. And this kind of plots that you plot, it helps you develop some level of intuition about complicated systems like that. So I think it was a good use of time, this entire hour, just showing different things you can do with SageMath.